谢谢大家，谢谢大家光临参与这场演讲，刘教授的演讲。最近 quantum computing 就是量子计算、量子计算非常流行，可能是继 AI 之后另外一个有突破性领域。包括Google 还有 Microsoft 最近都有新闻，是吧？量子计算公司的股票也涨得非常好，最近。今天我们非常有幸，请到刘教授。刘教授是现在在 NC State 是吧？做教授。刘教授毕业于，让我看一下啊，抱歉，毕业于清华大学物理系，然后呢又在那个布朗大学收到了硕士和博士学位，然后刘教授，然后就加入了 NC State 北卡州立大学。在加入北卡州立大学之前，刘教授是博士后，在 MIT 做博士后。所以今天我们欢迎刘教授来给我们介绍量子计算，谢谢。
谢谢。感谢这个徐主席邀请，然后非常感谢这个机会能跟大家交流这个量子计算的最近的一些这个基本的这个知识，还有最近的一些进展。然后我的这个 talk 呢，就前半部分应该都是比较基础的一些 background，然后后半部分的话，可能稍微会有一些比较专业性的东西，但是我基本上也都是想，我会 switch 成英文，就我自己对 ，OK。对，然后如果说后面就是有一些英文单词大家听不懂的话，需要中文翻译就随时举手就行，因为我们今天人比较少，大家就多 interactive 一点，交流一点就 OK。好，那这样的话，我就大概开始讲。So I will say this again in English. So we have just a few of us here, so let's just be interactive. Anytime if you have any questions, feel free to raise your hand. And the first part of the talk will be background, introduction to quantum computing as a field in general. And then the second half of the talk will be more sort of domain specific, and there might be some technical terms. So if feel free to ask any questions anytime. So in the first part, I will just focus on the first two questions here. What is quantum advantage, right? Why should you care about it? And then the second half is how to achieve it. So this will have a little bit of technical terms here. Let's see. Okay, so let's start from the first one. I wanted to draw a parallel comparison with AI or data processing because lots of us probably works on computer science, IT, and technical field. So if you think about what we have been working on, right? So we have classical computers, and then we have lots of classical data, and then in the bottom, this is like a 0101 bit, right? And then we have been studying a lot about how to use classical computers to process classical data. And now someone says, okay, now we have a quantum computer, and okay.
And then the screen is touch screen, so you can just swipe.
Oh, I can just swipe. Okay, that's easier. Try. Great. Yeah, let me turn off the okay here. Okay, great. Swipe back. No. It's only going forward. Okay. Okay. Yeah. So I'm gonna. Okay. So now, if you actually think we do experiment even in physics or chemistry lab, right? We are taking spectroscopy. Spectroscopy, lots of them are photons and electrons we're measuring, and those are quantum mechanical particles. So those data intrinsically are actually sort of quantum data. And we are still having been trying to use classical computers to process quantum data. But who says we cannot build, computers out of quantum phenomenon, right? So in the past, few decades, and then people have been started to think about how you can actually build a quantum computer. And if you have a quantum computer, now the data processing, computing landscape will change. So you can actually now use a quantum computer to process either classical data, and then that's all the data you're currently working with, the financial markets, the proteins. I'm going to give more classical data example next slide. And more interestingly, you can probably even think how to use quantum computers to process quantum data directly without converting those, into classical data. And this is the field that quantum computing, quantum information science sort of studies mostly. And there are many unknowns. And today, in the second half of my talk, you're going to see some examples of algorithms that we design on quantum computers that actually process quantum data.
What's the error mitigation?
Yes. Okay. So good question. So error mitigation here is probably a bit more technical term. So this so refers to some process where, let's say, you take a spectroscopy, right, and then your machine might actually have errors, and so that error will kind of corrupt the underlying actual data that you wanted to measure. So there is error that appears in a sort of a quantum data intrinsically. So if you use classical computers to process those quantum data, you have to convert those into classical data, which might have errors because of the intrinsic error. And now you have to think about error mitigation sort of strategies to correct those quantum errors intrinsically there. So think about this as like a classical post-processing algorithm that allows you to kind of get rid of some noise or errors in a classical data that was obtained from quantum.
Basically, the error is still there.
Yes.
The error is still there.
Yes.
For the class data, we are trying to kind of mitigate the consequences.
Yes. Yes. So if you know some structure of the noise, then even if the error is still there, then you can kind of find some way to correct that error or recover the underlying, true data, true information there.
But the challenge is it is like the nanoscope, right? Like
Yeah.
quantum level.
Yeah.
It's uncertain. You don't.
Yes.
It's really hard to know.
Yes. So in the quantum level, right? So this is the bottleneck of actually using classical computers to process quantum data. You have to measure, and then once you measure, you collapse the quantum data, and then you kind of waste the quantum data. You have to kind of get another quantum data. So the kind of nice thing about this is that a quantum computer just manipulates that quantum data directly. So you can just do your computation when the data is in superposition, kind of change the quantum data into another quantum data, and then in the end, you just measure that essential information what you want. So that's kind of defer measurement and manipulate the quantum data first using quantum computers, and then you kind of extract the information you want. But we'll see some examples later on.
Even we have an intrinsic error there, but it just process as it is.
Yes.
Any consequence.
It will. Yes.
Not as much as
I would say not as much. So if you have errors in quantum data, and then you convert those into classical, you post-processing, in general, you're going to need lots of overhead, classical overhead, computational overhead, expensive to correct those errors. But if you kind of try to design some encoding or do some extra things on the quantum side directly, then the overhead, the cost is not that much. Yeah.
Not that much.
Yes. Yes. So in quantum, those things, similar idea, but it's not called error mitigation. It's like called error correcting code or error correction. Yeah. So you kind of design some encoding scheme so that you kind of encode just the 1 qubit of data into a super large space. So when error happens, the error happens, then you can kind of correct it. Yeah, I'm not going to go into that error correction field, but yeah, thanks for the question. That's like a really big field now. And that's what sort of bridges us from the current noisy quantum computer to the future ideal fault-tolerant quantum computer. But, I probably mentioned something on that line. Yeah, these are all classical data, right? Examples of classical data. And financial market, protein database, or even temperatures, or even any sort of modeling, classical processing, time series analysis. And then the sort of hardware level, we're just using classical computer. At the bottom of it, it's transistors with some, controls and fault tolerance built in. So, but where is quantum data? I mean, anything, if you zoom in, this is us, like 1 meter, so this is length scale. If you zoom in like 10 to the 10 times, you're gonna be at the atomic scale and nanoscale, and that's where lots of the quantum mechanical phenomena start to appear, right? And in quantum mechanics, there is this equation that physicists discovered like over 100 years ago, a Schrodinger's equation that says that any quantum mechanical particle, its motion, its state, can be just described by a function, so psi, and then that function is wave function.
quantum
How does the wave function
quantum analysis
evolve over time? The dynamics of a quantum system is given by this differential equation. If you can solve this equation for a given
量化呢，
Hamiltonian, and this Hamiltonian
这是
describes
把这个
the
数据
structure
量
of your
化，
system.
跟
For
量子
example,
呀，
how
就
does
是
particle interact? You know, if you have two atoms, right? How does atom and electron interact? So that information is given by H. So then you just have to solve this equation, and that will tell you all the information you want about quantum systems. And these are examples like of maybe sort of spins in transition metals, right? All the metals have like d electrons, and they're unpaired. And then if you have a magnetic field, electric field, it's actually going to undergoing some quantum mechanical motions. And this is some spectroscopy with light and actually some gravitational wave detector that you use photons and lasers. These are also quantum. I omit the last one is actually from astrophysics. So you might think that black holes and all this stuff has nothing to do with quantum. But then actually Stephen Hawking said that black holes have this gamma ray emission. So gamma ray is like super high energy photons. And that's again sort of quantum data. So like if you actually look at the super large scale or super small scale, quantum mechanics is basically sort of appear everywhere. So the key features why quantum is unique and why quantum computer is powerful is really some special characters of this data. So one of them is coherence. So what does that mean? If you think about a microscopic object, right? So this is like Schrodinger's cat example. There's a cat in a room, and then there's like a poison, which can be triggered by some switch. And if there's a X-ray emission that emits some alpha particles that will trigger this, switch that will break this poison glass, and then the cat will kind of smell that and die. But if there's no X-ray emission, then the switch is off, and then this thing is like the hammer is up, and then nothing happens. The cat is alive. But because this X-ray emission, it's a nuclei sort of property, it's probabilistic, and it's not deterministic. So it may emit, it may not. So actually, the state of this emission is like in a superposition of emit or not. So as a result, this cat will be in a state of life or death. So it's weird that if you do not sort of open the box, you do not see whether this switch is on and off, right? You do not open the box and see. See means measurement. So you don't know what the cat is dead or alive. And quantum mechanics says that it's actually going to be in a superposition of alive and dead. So this is called coherence, and it's like it's a bit. It says it's actually both at 0 and 1 with some probability, and it never says it's whether 0 or 1 deterministically until you see it, you measure it. Okay, that's like one property, which is very important. You can think of this as a wave property, right? You have two waves and they superposition together. Now, the second property actually is even more unique. That'll give you a lot of computation power, which is called entanglement. So what is entanglement? Right, entanglement is this thing describes property of one object, this cat, on two different states. So entanglement says like the property of two objects, and then somehow their state is correlated in some fashion. And this correlation is not a classical correlation. So let me explain a little bit. Let's say, think about this object 1 as a spin, or as a quantum bit, which can be in state 0 and 1, or red and blue, okay? And the state of this thing, object 1, according to superposition, the coherence principle can be simultaneously red and blue, right? The state of 2 can also be simultaneously red and blue. But entanglement says that the two of them, the color is correlated. If you actually measure this particle 1 or object 1, you see it's in red, then particle 2 has to be in blue. And somehow if you see particle 1 is in blue, then particle 2 has to be in red. And you see that this is different from classical correlation, because classical correlation, you actually already specify a color to 1, and then you say your 2 is blue or red, right? But here, even 1's color is not specified. It could be red or blue, but like depending on what it is, then particle 2 is going to be the opposite color. So that's entanglement. Entanglement is some correlation that's beyond the classical correlation. And that also is the key reason why quantum computers have power. And if you actually think about the state actually now become a qubit, quantum bit. And then you have lots of this quantum bit together. That's a quantum computer. And then you can kind of manipulate this quantum computer in entanglement and superposition. Somehow that give you computation power. So these are the positive side, advantages. The disadvantages, I mean, nothing comes from like for free, right? And this state is very fragile. Although it's super powerful, but to build a quantum computer is really hard. And in this superposition, like cat is alive and dead, even if you have a small perturbation, like super small perturbation, you're going to actually force the cat to be either live or dead. You break that superposition, you make it deterministic. So that's the effect of quantum noise. And to actually make the quantum computer in superposition, you have to kind of isolate it from like environment. Even the thermal fluctuations, the temperature we have will break quantum computers. You have to kind of usually cool it down to super low temperature and then perform this, good quantum, preserve this coherence and entanglement and perform a good quantum gate. And so that's the downside that one have to kind of think about. And this error correcting code that you were asking is to kind of try to fight this fragile property to kind of make the state resistant to noise. Yeah. Usually, so it depends on the energy scale of your system you are using. For example, the qubit, right? There is 2 states. So if your environmental fluctuation is much smaller than this energy scale, then that's fine. Usually, right now, the operating temperature of the leading quantum computer is like millikelvin, or even like a Kelvin. Some of those even like a microkelvin. So room temperature 300 Kelvin, right? So this is like close to the absolute zero temperature of the universe, but you can still do it. That's why they use this like big giant dilute refrigerator to kind of cool down quantum systems. And that's why also US kind of does not allow China to kind of import the dilute refrigerator. This will make quantum computers easier to operate. Because because this state, this quantum property only happens at a very small energy scale. That small energy scale is so small so that like any small energy change in the environment will kind of be comparable to that small energy scale. As a result, then it's very sensitive. And if you have large energy, you won't see quantization, the quantum effect. Quantize only happens at a super small energy scale. So like I, as a human being, right, I'm moving, like my trajectory is all continuous because I'm like 70 kilograms and I'm too heavy. Like my energy is too large. If I'm just have a mass of electron, like 10 to the minus 30 kilogram, then I will be quantum mechanical. And yeah.
So the function of, if you take a function, the energy you use is very small.
Yes.
But in order to get this function, you need an environment use huge energy, like cooling down.
Yes. Yeah. Exactly. Yeah. Yes.
Entanglement, there's 2 questions. One is so it's not binary, so quantum state can be more than that 2 state of binary. And second, it's always the relationship. Even one proton is one state, and the other proton is always in the particular state. So that relationship is different.
So that relationship itself is deterministic only after you determine what's the first particle state. So I can also think about the, so two particles have a quantum state. I can also change this relationship. I can say if 1 is red, 2 is red, and then 1 is blue, 2 is blue. So that relationship is changeable. That's determined by the two particle quantum state. I can configure that. That's what I'm doing, sort of quantum computation. But once I determine what is the state of the first one, then the relationship is fixed. But like, if I do not measure, then the relationship is not clear.
To make sure I understand this, the state is still binary, still 0 or 1. But all the 0 1 is not hard coded or predefined. It's more dynamic, right?
So actually, this is, I would say the state itself is not 0 and 1. The state itself is in a superposition. It's some quantum state. So it's not different from stochastic probabilistic classical computing. So probabilistic classical computing says, okay, you actually don't know your transistor is on and off. But that's like with probability 0.1 on and 0.9 off. Quantum is different. Quantum, it says, it's actually the square root of the probability with some phase. And it's in a superposition of 2. I don't know what's a good way of describing that. So using classical intuition, but that's what quantum mechanics says. Only when you measure, so you look at that particle, that converts that square root of p into p, the probability. So after measurement, quantum is similar to probabilistic classical computing. But before measurement is something different. Yeah, this thing is like non-intuitive.
Distance, right?
Yeah.
Irrelevant, right?
Yeah, exactly. Yes, so this distance is irrelevant. For example, I can entangle these two, like in this room, and I send one to the moon, right, through some channel. And then that entanglement is still there, if you don't have noise. But most likely, when you send it through the channel, you will break the entanglement. Yeah, so that two property, if you kind of use that to do computation, and then that's the theme of a field called quantum information science, if I add engineering, and what that does. So it's, definitions like combine the law of quantum mechanics with the information theory and technology to advance the development of transformative computers. This is computing. And sensors, like you can use quantum to do sensing. And networks, you can use quantum to do communication. And even in encryption, you can use quantum to kind of break the RSA, factorize a big integer. And so this is like just a schematic of saying, if you actually start from quantum mechanics instead of classical mechanics, then you can study how information is processed in quantum computers with the law of quantum mechanics. And then there's all sorts of different applications along the 3 major domains that I mentioned. So in the second half of my talk, I'll probably talk about computing and sensing a little bit, and network and encryption. I don't do too much research on those areas, so I don't feel like I am a good person to talk about those. Any questions about this in general?
Yeah, but the quantum computing computer.
Yeah.
How long the stable state can be maintained?
Yeah. So I will kind of mention that. Do I have that somewhere? Yeah. So maybe I'll just go here. This is all the available roadmap of the quantum computing companies we have. For example, IonQ is next door, like Duke funded and located regionally. I don't know if we have audience like working with IonQ, but if this is like Continuum, another UK company, if you see their 2-qubit gate error, so this error is roughly right now like 1 error per 1,000 gate. So that means like the lifetime, it differs from depending on what physical platform you use to realize the qubit. But roughly, the lifetime can range from like microsecond to even minutes. And the gate speed is also kind of differs. But this error rate kind of give you a sense of, you can do 1,000 gate, for example, before 1 error kicks in. So that means like 1,000 gate computation is probably error-free, which is perfect. And this is like improving. So the first row is qubit count, right? So 2020, they have like 20 qubits. They wanted to scale to 50 and even 1,000 in 2029. And then they wanted to kind of reduce the error rate to 10 to the 4. That means you can actually do 10,000 quantum gate without an error. And this third line here is logical qubits. Logical qubit is like when you actually do a layer of error correction. So you can, for example, the physical qubits is 1,000. You basically have like 1,000 spins or physics qubits. But you can use 10 physical qubits to produce one low error rate like logical qubits. And so then the logical qubits error rate is kind of suppressed, right, compared to the physical error rate by 1 order of magnitude, or even so, smaller. And so that's like a roadmap of Continuum. Continuum is making this trapped ion quantum computer. They kind of cool down like small individual atoms, like to super low temperature in microkelvin. And then each ion is basically a qubit. And then you can kind of manipulate some two-level systems energies within the ion to do a qubit operation. Yeah, so this is like, maybe I will just finish this. This is IBM's roadmap. And I don't have the sort of specific numbers here, but you can see here by 2033, they plan to have 1,000 logical qubits. This is a very ambitious goal compared to that. But, Yes. Yeah. Yeah, right now it's not unified. We have all sorts of different things. So let me see if I have that slide. Okay, so I'm actually gonna maybe jump a little bit. See if I have, yeah, so I would just say this, right? So this is like a physical layer, how you actually make quantum computers. This is literally a photo of the IBM's sort of quantum computer. It's all of this lines, all that is electronic signal control. And this thing is a vacuum chamber. And inside that, it's like a cooled down small superconducting materials. And they kind of cool down below the transition temperature. There's like a Josephson junction where there's some metals and insulators. And then you can kind of turn a single electron through the insulator, a super thin insulator. And that is like one of their qubits. But Continuum, for example, using trapped ions. So this is, again, some electrode. And then each one of the red dot here is a single atom. And then the atom is charged. So they have Coulomb repulsion. They won't kind of combine together. They're just going to sit there. They are being trapped. And then you can use laser to interact with each one of the atom individually. And this one is a laser. And there's some other company, for example, Nord Quantique in Canada. They kind of just make quantum bits out of photonics. And this one is spin, So right now it's not unified. It's like the pre-age of digital quantum. We don't know what's the best way to scale up. Like everybody's trying to kind of scale up on their own platform. They believe their roadmap is the best one to actually go forward. See if I can kind of just go back a little bit. Okay, so with that background information, I think I can talk a little bit about quantum advantage. So in the end, what you care about is probably given a problem, like any problem you want to solve, you measure the runtime of the computer you solve that problem as a function of the problem size, right? So for example, in a factoring algorithm, the size is like how many bits are there to represent an integer. For sort of search problem, let's say you have like n items. There's one item that's marked, or that's what you want. You want to kind of just brute forcefully see which element is what you want. So then their n is like how many elements are there to search from, right? So you can always work out like a given algorithm. What's the scaling of the best sort of classical computer algorithm to solve that problem given a different problem size? And there are some problems super hard to solve, so that the runtime actually increases exponentially. And then for those hard problems, quantum computer, people find the quantum algorithms where the runtime actually increases really mildly as the problem size increase. And so as a result, there will be a crossover somewhere anyhow. And beyond that point, for those kind of large problem size problems, quantum computer will actually solve the problem much faster than classical. But below that crossing point, maybe there's like no advantage. So this is maybe like a definition of quantum advantage. And the known, you can prove that groupers, Shor's, factoring, and for simulating dynamics of some quantum systems, there is like a provable quantum advantage. And we also hope that optimization and machine learning, right? If we put those on quantum computers, will have advantage. Yes.
So I have a question about the yellow line draw.
Yeah.
So are you sure that quantum computer will solve all the problems?
No, it's not gonna. Yeah, this is just the.
For those list of problems.
Yeah, this actually just a schematic.
Okay.
And the next slides, I'm gonna give more different curves. Yeah, but so yes, for this 3 problem, for example, we know the precise scaling. It's not actually a linear line, but it's mostly a polynomial line. And then so for classical ones, we know this. Groupers is still polynomial, but it's higher order polynomial. And the Shor's and the quantum simulation is all exponential or sub-exponential, close to exponential scaling for classical ones. Yeah.
Why in the small problem size is classical computer even better?
Yeah, so this is a really good question. So the classical computers is so good now. We started to making those like 1950s, right? And then we already have like 70 years working on classical computers. We're improving material and gate speed and error rate. So the classical bit error rate is so low. It's like 10 to the minus 20 something, right? 30s. And the quantum bit gate speed is so slow. And their error rate is also very high. So it's like the hardware on quantum is so slow in a primitive stage. That's why there's like a big constant prefactors here that makes.
It's not theoretically, it's just more, it's like mechanically or something.
Yeah.
It's you can improve. It's for theoretically, quantum computer can be better than the classical computer, even in a small size of the problem.
Even in a small size, theoretically could be, yes, if we improve quantum computers' gate speed. Yeah. So this is actually a good question. So computer scientists, right? So when they kind of think about problem, they wanted to think about asymptotic scaling, like in large problem size. But practitioner, right? I don't really care about super large problem size. Maybe I just care about whether I can solve this specific problem. Then I actually sometimes care about this region a lot, then like this region. So if I care about this region, then I would have to actually assess the constant factors, how fast the quantum gate is versus the classical gate speed and how much I can.
Big question is, quantum computer can be replaced of the classical computer.
No.
That will be change of the landscape of the industry. That's question. So if you cannot, okay, so each one have own territory.
Yeah.
But it's I think it's not about whether it's solved, it's more about cost. Right? Quantum computers, so right now this the cost is just extravagant. Even if you can solve it using quantum computer, you already can use a classical computer to solve. Why bother?
Yeah, if theoretically you can solve this problem, but is this just industrial scale? So if you do industrial scale and it's a change of the scale of manufacture, or you can achieve in the future.
But physically, this is impossible. You need to maintain the low Kelvin, the temperature that inherently costly.
Yeah.
But there are certain issues, right? They are deterministic, like addition, right? 3 plus 5, right? So those kind of questions, even say for big numbers, still is deterministic. There's no advantage for the quantum, right?
Yeah.
It's really kind of for those kind of problems.
Yeah. So Yeah, so I should say, like, for my belief is this is like hard to prove for any problem, right? So my belief is that, of course, quantum computer will not replace classical computers. No, there are some problems quantum computer can never have speed up as compared to classical. I mean, some problems quantum computer will have, and what we believe is, I mean, the well-known is these three examples, but the quantum simulation is actually a big class. If you think pharmaceuticals, all the industries, right? Any property that relevant to microscopic molecular interactions, and lots of those are quantum, but of course there are some classical phenomenon going on as well. But the hopes that, people think quantum simulation is actually one of the biggest sort of applications.
So I think some was
Yeah.
computer science and optimization background. So one of the challenges with the classical computing is we call it those big O notation to measure how complex the algorithm as the problem size becomes bigger. It's just way exponential growing. The complexity grows faster than the size, and now it's not a polynomial.
Yeah.
Right? From the classical computer, if it's a non-polynomial, how to translate that to become polynomial in the
quantum. Yeah. That's the problem of quantum algorithm design, right? It's really case dependent. If you say you give me a classical problem optimization problem, I would have to look at that problem and then see if I can find a quantum algorithm that achieve low polynomial scaling or linear scaling or even logarithm scaling. Like, there's no universal rule that can translate any classical algorithm optimization, for example, into a quantum algorithm. Most likely, the quantum algorithm will be looks very different from the best classical one, because the two computers are just operating super differently with different laws. So yeah, so it's hard to kind of translate directly, but.
So I think, even though you list those applications, I
Yeah.
think they are kind of at least two different categories, right?
Yeah.
Like the global search and the Shor's algorithm. They are algorithms trying to speed up the process or whatever, right? But the simulation, on the other hand, is different. It's not like optimization, but really because in the classic, how do you describe, in the classic computing, how do you describe or simulate the quantum level or the narrow level of electron interactions?
Yeah.
It's a simulate, but quantum is kind of a native features to do that, right? So that's different.
Yeah. So that's a good comment. There are like maybe a subclass within quantum simulation. Some simulation is more analog quantum simulation. You kind of just engineer your quantum system, mimic whatever quantum property you want for a system you want. And the other is like digital quantum simulation. Now, digital simulation is much closer to the classical way you actually simulate. Yeah. So it's also using gate. You discretize the problem, you do digitized simulation. But even in that case, you can still find, lots of those are exponential speed ups when you even do digital sort of simulations of quantum systems. And then, so this is like a Richard Feynman, and we probably know this a lot of times. And the motivation that he wanted to make a quantum computer was for solving the simulation problem in the first case. And this is probably more technical things. So you can, like, from computer science perspective, you can actually work on computation classical complexity theory, and then see what kind of problem is solved on classical computer efficiently. Efficient by definitions, in polynomial time as system size increase, and that's the P category here. And similarly, for quantum computer, you can ask what class of problem can be solved in polynomial time on a quantum computer. That's the BQP class. And then it's believed that BQP is bigger than P. So like quantum computer is like more powerful than classical one. But there is also this NP class of problem which is cannot be solved by classical computers in polynomial time. And this is like hard problems for classical computers. But you see that this BQP actually can cover some problem even in NP. And those problems like the key that we wanted to find the quantum speed up, which is hard for classical computer. But then still like simpler that can be solved on quantum computers. And this also says that in NP class, there are problems that cannot be solved polynomially timed on quantum computers even. So there are some problems even both classical and quantum computer cannot solve, efficiently. And then in NP, there is a small class of problem called NP complete, which is the most difficult problems in NP. And if you kind of solve this small class of problems in NP complete, then you can solve like all the problems in NP. And then like even outside of NP, there's like even more difficult problems that people have. And so like, given that, maybe it's a more rigorous way to kind of draw lots of different scalings, right? Saying like what's your computation times as a function of input size. And then there's factorial, exponential, sub-exponential, high order polynomial, low order polynomial, or even logarithm or constant. And so there's a hierarchical of, speed ups that one can say. So this plot, is effort by Microsoft trying to quantify really for what problem, how long, how many qubits do you need to solve those kind of problems. The sort of vertical axis is here is the physical qubits number, and the unit is in millions, not in one. Okay, so the runtime here is in seconds, but then you see minutes, hours, and days, right? So there is the factoring algorithm. Unfortunately, sits somewhere here. Like it's gonna take like weeks to even decades to solve, depending on what is your gate speed. Gate speed. And error rate. So the first unit here, microsecond versus nanosecond, is your gate speed. One gate, how long does it take? And then the second number here is your error rate. So if you have a low error rate versus a sort of high error rate, the cost will be different. Okay, so you can see that this roughly takes even like 10 million qubits and years, very hard probably. Quantum chemistry takes also a lot of time, but I think this is a subclass of quantum chemistry, and you can simulate chemical dynamics, which will be sitting here. But this is like a very special chemistry problem of preparing ground state of some electronic systems. And the more useful kind of near term, advantage is this dynamic simulation. It's the quantum simulation problem. From this gate count, if you have roughly like 1 million physical qubits or even 100,000 in this line, and then you can solve some useful problems in minutes or hours on quantum computers. And this scale is kind of closer to the roadmap that this quantum companies put out by the end of this decade, like in 5 or 10 years. So hopefully, in 5 or 10 years, we can actually solve some very meaningful problems in dynamics. Yeah. So I will show some toy examples. I will also mention some, some more specific examples. Okay, that's all background. So I will now actually talk about how to achieve this and give you, more detailed examples. And this one we already mentioned. Obviously, how to achieve quantum advantage, you're going to need to start from hardware level in principle. Actually make the processor, actually design the algorithm, and then write down the software, and now find the applications, right? That's all what we did for classical computers. And actually in the quantum case, it's probably similar. My research focused a lot on this algorithm side of things and applications. And I do talk a lot with experimentalists how to actually improve their experiment fabrications or design and gate and all that. So I'm gonna try to give you a little bit of background, just like more technical quantum computing. A short version of this is for us, we know classical computer. It's a classical reversible computation. It's not the classical computer we know. Quantum computer is all reversible. If you can run it back forward, you can run it backwards. Information is preserved. And then now, based on that, so you wanted to turn the inputs of your classical computer, like 0 and 1s, into coherent superposition of all possible 0 and 1s. That's what we mentioned before, the superposition, okay? And you feed that into a classical reversible circuit. And of course, that circuit now is realized by a quantum computer, quantum mechanics, so that it can take input as a coherent superposition. And then after the computation, you measure. So measurement is like collapsing the coherent superposition. And then the computation is kind of changing in what way the superposition is at, how the entanglement is at. And maybe like that's one way of saying that. So these are all, even the classical gates, right? You actually have. And so this gate, this is not reversible because you have 2-bit input, you have 1-bit output. 1 bit information is erased, but that's what we use because this is more efficient. But this gate does not exist on quantum computer. This gate, on the other hand, exists on quantum computer because the input is 2-bit, output is also 2-bit. You do not erase any sort of information. And you can kind of actually show that just all the classical reversible gate have a quantum implementation so that any classical reversible computation can be kind of translated into quantum one. So maybe I'll back up what I said, saying that there's no universal we can translate. If you can write down a classical algorithm, like literally into a reversible classical logic gate, and then I can turn that all into a quantum realization of that classical reversible gate. And then I will have direct translation, but I don't know if that will have speed up or not. And then that's something that will have to be.
Called gates. What's the name?
You mean gates? Yeah, gates is like 逻辑门操作. It's just operations. Oh, double E 里面语非门 sorry. It's not Bill Gates. Yeah, it's logic. So quantum actually you need to define this gate to kind of see how you manipulate a quantum bit. So this is just a slightly more linear algebra thing. Let's say I have a qubit, right? Qubit is a 2-level system. I can represent that as a length 2 vector. And 0 state I can represent as 1, 0. And 1 I can represent as 0, 1, okay. And now how can I represent the state of a qubit? It's a complex number. Multiply that 0 vector plus another complex number, multiply the 1 vector, right? It's just like a dimension 2 complex vector space. And that's my wave function. That's like any state of the qubit I can be on. Now I need to define quantum gate on this qubit because this is like a 2-dimensional vector. Then any gate that transform 1 vector to another necessarily will be a 2-by-2 complex matrix. And that matrix, quantum mechanics says that matrix have to be a unitary matrix. The unitary matrix can always be written out as like e to the some imaginary times some Hermitian matrix. That's all quantum mechanics says that. And you can write down the most general way of writing down any 2-by-2 unitary matrix. And that's the most general quantum gate that you can have. So the theta is like a rotation angle you kind of tunes. You can view the state of a quantum bit like as a point on the 3-dimensional sphere. And then all the gate you're doing is just moving 1 point to the other. Right? So that's how you manipulate the state. B is tunable, it's like unit 1 3D vectors. And theta is continuously tunable. So these are all continuous gate. And then the sigma is called a Pauli matrices, which basically expand the complete basis for 2-by-2 Hermitian matrix. Not important, okay? And so I would say, that's how you actually define some quantum gate. And actually on experiment, on quantum computer, you control your parameters, voltages, signals to realize a specific theta and a specific B. That will turn a quantum state from one to the other as you wish.
So in terms of the quantum gate now, those numbers they are not binary.
Yeah, these are actually continuous numbers.
Continuous number. I think that's the advantage. With the classical, everything is a binary.
Yes, exactly. Yeah.
So on the website, right, the quantum states.
Yeah.
They want.
Yeah.
Square, they want what
Has to be equal to 1.
Right?
Yes.
And these are the probability.
Yes.
But what is that R?
Which are? This R.
Yeah.
Yeah, this is a notation for a quantum gate.
Notation.
Notation,
Oh, notation.
a symbol.
Oh,
The reason why it's called R is because of rotation, R. Because you can view this like quantum gate as a geometric interpretation, is that any state lives in a unit sphere in 3-dimensional. And then a gate just moves that state, rotates that state anywhere on the sphere.
Which is really determined by the state, by the
And the B. Yeah. So if you learn sort of classical mechanics, you have this rigid body rotation, right? If you have anything, you rotate it along X or rotate along Y. That's like how you can visualize this quantum actually. So the 2x2 complex matrix is equivalent to 3x3 real matrix. The 3x3 real matrix is describing how we rotate a rigid body, right? So that's how you kind of visualize this thing. Yeah, so like these are measurements. So I probably gonna use some kind of this notation. This is called a quantum circuit. So what that says is every line represents a qubit or a subset of qubit. And then this box is a gate operation I'm gonna do. And then this is like as time goes on, what happens on my quantum computer, right? So it's like a clock, like every time I do a gate, and then after that gate, I do some meter. So it's like meter, which is like measuring my qubit. After measuring that qubit, this will kind of collapse to 0 and 1. And I might have some quantum state I don't measure. That may be some state actually I want as a result of my computation, a quantum result of my computation. And so this state could be a ground state of a molecule, benzene molecule that you wanted to prepare on a quantum computer. So you just have to design that circuit.
That's computer, we have the frequency, gigahertz.
Yeah.
This one from based on the T from 0 to 1.
Yeah.
How frequent?
Yeah, you can also have frequency. Right now, the gate speed is actually very low. I think not gate speed, but clock speed. I think roughly, probably you can just do kilohertz or at most megahertz. It's probably very hard to do beyond that. Yeah, that's gate. Okay. So there's a slightly non-trivial thing here that I said R is continuous. That's where the power is. But actually, to make things fault tolerant, you have to discretize this R into some discrete gate. Because only when you discretize things, you can make those things robust against noise. If you always use continuous number, I mean, whatever you say that number, I can always have very small perturbation around that number. So it will ruin my computation. So I actually have to have this discrete gate. And this is the non-trivial thing about sort of quantum computation theory. It says that if you just have these two discrete gates, like Hadamard gate and T gate, which this is their matrix, very specific, you can approximate any continuous gate RB that you want to error, some arbitrarily small error epsilon by only logarithm of this number of T and H gate. So this is like you're using discrete gate to approximate a continuous gate, but you can make the approximation error exponentially small by using slightly more discrete gate, which is entirely not obvious. And why this 2 gate is sufficient? There's a proof, but I don't have an intuitive explanation to that. But this is actually the key that makes fault tolerant quantum computer possible. If you always have continuous, then you cannot do fault tolerant.
Yeah, sorry, this question may not be directly related to
Yeah,
this.
no.
I just I'm just curious, like each qubit state, you said it's continuous and translated to discrete steps. So how many steps is it translated to? Like 10 or 1?
Yeah, so the qubit state here, this is always like a 2 by 2, 2 vector, dimension 2 vector. What I'm discretizing over is the gate parameter. So the state itself is still there, like it's going to be superposition. But whatever I'm discretizing over is the gate. And when I discretize, the state doesn't get copied. It's still that same kind of dimension state. But I don't know if that answers. Yeah.
就是说我们不是说这个一个量子比特，
对，
它是相当于它的状态是一个连续的状态，是吧？
一个量子比特，对，它状态是一个连续的状态。但是如果你 discretize 这个 gate，其实你能看到它的状态也会变成 discrete。但是这个 point 就是你能够通过增加这个 discrete gate 的这个数目，让它变得越来越连续，越来越连续。然后它变得连续的这个速度跟你这个 discrete gate 的数目增加是 exponentially 增加的，就非常 efficient 让它变得连续。
对，那这个 discrete 的状态有一个范围吗？
对，如果你 fix 有范围，如果你 fix 这个多少个 h 或者 t gate 你用，那它最终就会有一个 lower bound， 你不能比那个更连续了。对，它最终你可以说它最终依然是一个近似连续，但是它依然是discrete， 但是你可以让它变得特别特别连续，然后你只用一点点的 discrete gate 就可以让它变得特别特别连续。对，但是我觉得在那个 classical computer 里面没有这个 theorem， 就是你可能要 epsilon 的 distance， 你需要是你的这个 discrete gate 增加是 1 over epsilon， 而不是 log 1 over epsilon。所以这个是一个 quantum 里面是一个 exponentially converging speed。对，这个就是让 quantum 比较 powerful 的一个。Anyhow, too theoretical. So maybe talk about some applications. I don't know how much time we have, so I'm gonna try to 5 minutes, 20 minutes. Okay. Okay, okay. I'll try to wrap up maybe like quickly 10 minutes, or and then we can have some discussion. So the application I will mostly talk about is quantum simulation, and I'm gonna talk about mostly how you simulate this kind of chemistry, quantum chemistry or chemical physics problems. And you know, we have, like in chemistry, right, lots of nuclei motion and electron motion. When reaction happens, it's really electron moves from one place to the other, bond breaking. When you have, this is like a picture of sodium chloride, you put it in the water, right? How does that dissolve? And most of this involves classical motion, but you know, the interaction between water and the sodium ion is like lots of quantum polarization happens. This is like spectroscopy. You have transition metal perovskite materials, special class material with transition metals. You can use light to drive some you know, property change of the materials that will be good for solar panels and some other things, right? You actually care about what's the band structure of this material, what's the excitation gap, energy gap, and how does electron transport in this material. And like this is another example of chemical reactions, and this is one example of a dynamics. So someone asked quantum dynamics. So this is a molecule that's probably appear in some drugs in organic systems. And this particular paper, I mean, they do experiments. You can kind of remove one electron from this molecule. And then this is the wave function of that electron you remove, the hole that you created. And then as time goes on, so this is like 5 femtosecond, too fast. And you will see like this whole distribution will change. And that whole distribution basically tells you where is the positive charge I kind of localized, right? So if the distribution is changing, you know that the positive charge is kind of moving on this molecule. That will change how this molecule interacts with some other molecules. So on a microscopic level, you just kind of think all this super fast dynamics kind of affect the slightly macroscopic level. You know.
This is generated by using quantum to simulate the world.
No,
Use the classic.
no, this is actually in a real physical lab. You use a laser, you prepare this molecule. And this is, you know, you use lasers to knock off the electron. So I'm saying that this is the target that we want to simulate on quantum computers. And I will give you one example, like a toy example, how we can simulate this for the hydrogen 2 molecule, not this big molecule. Very theoretical, but electron and nuclei motion. Okay, so that's what we care in quantum simulation mostly. And there's some approximation you can do. For example, you can ignore nuclei motion because it's too heavy, and electron mass is too small, and nuclei mass is roughly 1,000 times bigger than that. The nuclei moves moves very slow compared to electron. You can just focus on electron and ignore nuclei. So if you focus on electron, then some applications of this is really just the electronic structure, which describe how electron forms chemical bond, and what is the, if you are in materials, what is the excitation band gap. So every line of this is the motion energy of electron on the materials, and actually the energy will be discretized. And you know, from like research perspective, you wanted to understand if you are given a laser to interact with the material or the molecule, when your laser frequency matches with the this energy level, this band and that band, you can excite that material. If it doesn't match, it cannot. So if you can actually calculate or compute this band structure, then you will understand the response of that material or molecules under light. So that's like called electronic structure. So one of the things we did is, if you wanted to solve the electronic structure, right now this molecules is kind of big, but your quantum computers is very small. If you look at, you know, this kind of big molecules, organic molecules I wrote here, you're going to need thousands or even more qubits. But one thing you could do is to do some divide and conquer. So you can say that, let's say you have a molecule. I'm just using a chain here, but you can isolate part of the molecule and break that into many, many small fragments or pieces. And then you can use a small quantum computer to solve each pieces separately. And then after that, use some quantum gates or circuits to kind of glue together the solutions of each piece together. And then you can do that self-consistently, which will allow you to tackle a large molecule electronic structure without, you know, actually using the super big quantum computer, but with a lot higher accuracy compared to some classical solvers. And this is one example I'm gonna kind of show here on a charge dynamics. This is all toy example because we are really limited by hardware now. If I have a hydrogen 2 molecule, like 2 atoms sitting there, I have 2 electrons. And of course, the equilibrium condition is that everything is, electron is going to be in the center, right, forming that bond. But if I drive that electron, move 2 electrons on the same atom as the initial point, then the charge will start oscillating between the 2 atoms. This is like, you know, a little bit of toy, you know, example compared to mimic some initially non-equilibrium sort of state, right? And then you can monitor how many electrons are there on the other atom, right? So, and then these are all kind of simulated quantum on the quantum computer. So if you see how many electrons are there as the time goes on, so this is also kind of 5 femtosecond dynamics. You can design some nice quantum algorithm that has super high accuracy, so that you can actually simulate this dynamics evolution as time goes on. And there's sort of different versions of that quantum algorithms you can do. And one of them we kind of come up with have a really good scaling complexity in terms of simulation time, which is linear in time, how long you want to simulate that dynamics. And for error epsilon, you only need logarithm of 1 over epsilon. So gate count, not 1 over epsilon. And delta is some success probability. So if you run your quantum algorithm, your algorithm may actually fail. So it's not, because everything is probabilistic, you won't guarantee that you always have deterministic algorithm. But you can actually kind of successively improve that success probability by using slightly longer algorithm. And that improvement is also on exponentially improving the success probability. So the algorithm itself here is very theoretical, but the point is to demonstrate that this theoretical algorithm have really good, scaling for asymptotic problems if we have, big quantum computers to tackle dynamics. I think I'm gonna actually skip lots of this. I will spend some time, talk a little bit about photonics and analog quantum computers. So on classical systems, we have gates, digital, but actually we also have analog devices, right? So lots of them, for example, this is LC circuits. You can actually have analog continuous oscillators. And we use this for amplifiers, for many other things. And on quantum case, all we talked about is qubit, which have discretized two-level systems. The natural question to ask is there an analog of a quantum analog devices that you can use, which may be good or even more powerful than qubit on some circumstances? It turns out that you can actually quantize these classical oscillators. So any sort of classical oscillators, when you cool them down to very low temperature, again, their energy level will become quantized. So this is a pendulum, also classical, but when you actually cool them down to low temperature, you're going to see that this is the parabolic sort of harmonic potential, right, as you have had in the classical X square. But the energy levels will be discrete. It's not going to be continuous. As a result, one oscillator will actually have, infinitely many or a lot of energy levels, which is different from qubits. One qubit only have 2 energy levels, 0 and 1. But one oscillator, quantum oscillator, will have, many energy levels. And every level now can encode some information. And you can actually just manipulate this quantum oscillators to do some interesting computations. And you ask, okay, where is this kind of quantum oscillators appear? Actually, they're almost everywhere. If you have some lasers, you trap those in the cavities, you can manipulate photons. If you have some phonons, you can drive the phonons in materials. And so all these photonic things is very useful resources as well. Now, what we don't know is actually how to use them for computation. Like just as the same way as you define some gate on qubit, can you actually show that there is a similar gate set on photonics, or even can you hybridize this photonics things with qubits to do computation in one setting? And actually, there has been lots of work on this. The answer is, of course, yes. You can kind of trap one atoms into optical cavities, and then you will hybridize these qubits with a cavity mode. You can come up with some aluminum boxes and inject molecular photons inside it. So all of that is, doable. And so what we did is basically to ask the question, like, can you answer about their computational power of these hybrid devices or oscillators? And turns out that you could actually work out a whole hierarchy of quantum computing sort of a stack if you assume you have given this hybrid oscillator and a qubit quantum devices on the physical layer. And then you can produce this in the experiment. And then we have some experimental collaborators that does that. You can design some standard gate set as you did for qubit, the rotation gate, the Hadamard gate, T gate. You can come up with similar ones on oscillators. And then you can design even compilers that actually translate like high-level circuit algorithm to concrete gate set on these hybrid devices. So we just have like a compiler sort of framework from this. And then you can even sort of design some programming languages for this hybrid devices. And then you can design algorithms on hybrid things by generalizing lots of the qubit algorithms to the hybrid setting. And so all that allows you to actually solve some problems that was really hard to solve on qubits. One of the problem is simulating, again, quantum simulation, but simulating some problem that is not only electronic, but has some oscillator, bosonic matter, degree of freedom in itself. So these are electron phonon couplings as example in materials or electron vibration coupling. I don't think I will really have time to kind of delve into this, but a high level message is that given this model, instead of mapping both the electron and the vibration to qubit devices as you usually do, what if you actually map your physical model by mapping the fermions to qubits, and you can actually map the bosonic degrees of freedom, the phonons and vibrations to the quantum oscillators you have on your devices. And then you can do some gate on the hybrid devices. And you can show a huge sort of improvement, compare the qubit gate count versus the hybrid devices gate count. For example, if you just wanted to simulate a single gate on the oscillator device, it's like this is one operation on the oscillator device. The cost is 1, so this is the gate count. The green is the gate count. But if you wanted to simulate that operation on the oscillator, on the qubit devices, you will see that the gate count, you're going to need lots of entangling gate and CASTNC gate. So this like overhead is roughly like 10,000 almost. So you can generalize this to like more complex mixtures of electron and bosonic matters. So I think I'm actually gonna stop here a little bit, and then there is some interesting things about sensing that you can do with photonic devices if you actually have this computing control abilities that established on hybrid devices. So I will stop here and see if you have any questions, so we can have more discussions. And so my conclusion will be that I hope I give some general background introduction to quantum computing that's helpful to sort of us from different fields that can kind of think what's the opportunities of quantum in our own fields. And then I introduced this kind of new computing platform that has qubits and photonic and the quantum oscillators that can do even more powerful things than qubit alone. With that, yeah, I wanted to thank you for your attention. And this is my contact info. Feel free to kind of write email or reach out. I have WeChat and anything, so we can have more discussions. Thanks. Yes.
So I'm curious about AI. So I'm just wondering whether like you have done something related to AI and quantum computing.
Yeah, so right now we are having some discussions, but I don't have work published on AI and quantum computing yet. Yeah.
Another question is like I guess US and probably Europe and probably China are all working on quantum computing. Are they going in the exact same direction, or are they like deviate a little bit? What are the differences there?
Yeah, it's a good question. I think it's a very hard question for me maybe to answer. I think, you know, I can see lots of the common themes that everybody is trying to work on improving quantum hardware to scale up to big quantum computers. And there is a lot of theoretical and algorithm design work that's going on in both 3 places. I think China probably lead in quantum communication at the beginning because of lots of prominent scientists. And now lots of effort I think goes both in computing and communication. And there is lots of sort of technology barrier that's being created on the government politics level. And so everyone basically is pretty isolated, especially China and the US. For example, I think Chinese research cannot access US quantum computer hardware. And so they actually have build up their own quantum hardware. And there is communications and conversations going on, but given lots of restrictions, I think everyone basically need to kind of tackle all the areas of quantum computing themselves.
The conceptual feature,
Yeah.
even the coming with quantum computing, seems like the competition landscape into fast computing and quantum computing coexist.
Yes.
For somewhat heavily.
Yes. Yes. So I think maybe not even in the future, like forever, there'll always be classical and quantum coexisting. There is a work by IBM last year. So they show that you can use a quantum computer to solve a really large molecule chemistry problem. But then they also need actually Japan's Fugaku supercomputer to do classical processing, like together with a quantum computer. And so I think that's a good point, and it's going to be there for a long time. Yeah.
Okay, I'm completely not in this field.
Sure.
Okay, but come with very general question.
Yeah.
I don't know if my understanding is correct.
Yeah.
Okay, for the quantum computer using is use small because they use very small energy.
Yes.
So they could be potentially could have a lot of application because they use small energy. But in order to use the quantum computing, you need huge amount of energy to support the system because the variation will be the big impact on the quantum computing use.
Yes.
Okay. So what is really advantage to use the huge supporting system to support the small things?
Yeah.
They have good potential.
Yeah.
Is the economically?
Yeah. So
makes sense.
Yeah, that's a good point. So I would say that it depends on how the support on energy cost scales as problem size again, right? So it matters if it's polynomial scaling or exponential scaling, and I think we can separate two things. One of them is the computation power of quantum versus classical. The other is economic value. So there's no doubt that computational power-wise, the whole field thinks that quantum computer has an advantage, and there are concrete examples that supports that claim. But the economic value will have lots of nuances. For example, the cost of actually making this quantum computer. Is it worthwhile to solve some problem that will have market value that can return the investment on actually the original way of fabricating those quantum computers? So I think the economic value is more tricky, and it's not clear. People ask killer apps, right? So different people have different definition on killer app. Some people think killer app is the economic value. Some people think killer app is the exponential speed up. So the economic side is a bit tricky, I agree. I think the energy cost is a really good point, and that's like something new direction that the field is trying to think now.
Until the energy cost problem is solved.
Yeah.
The quantum computer widely used quantum computer could be limited on more like research scale instead of industrial scale.
Yeah.
That's correct?
Yes. But you can also say the same thing for AI, right? So all the large language model, I mean, like how many powers they are consuming? Is quantum computer even consuming that much? I don't think so.
好了，我们再次谢谢刘教授。
好，谢谢大家。
好的，
哦
quantum computer。
好，谢谢谢谢谢谢。
这个有点像这个 IBM 的那个